Would you have the courtesy to close the door? That would be nice, thank you. So I'm not giving a real-time talk today. Actually, NAND flash is my hobby. It was the first project I ever contributed a larger part to the kernel, rewriting and refreshing the NAND flash support. That turned out to be an interesting challenge over time, because NAND flash is, say, clearly crap. So let's look a little bit at how UBI is embedded into the kernel. So if you look at the flash device, then we have the MTD subsystem where we have the raw drivers, the drivers which access the NAND flash controllers or magic bit toggling thingies. So you can partition out your flash in the MTD layer, and then on top of an MTD partition you can put UBI. UBI is basically a logical volume manager for flash. The nice thing is, or the bad news about MTD partitions, they are fixed. It's really hard to reconfigure them on runtime. So usually what we do, if we boot out of NAND flash, we have this one partition where the bootloader sits because you can't move it, because the hardware expects that it's in the first erase block. So one interesting observation, and I got asked this question several times now. Flash gets more shitty over time, yes, that's true. But one good news is they keep the first erase block intact. So the first erase block, even on multi-level cell flash, is a single level cell flash. So that's just that you have a decent chance to get even into booting. So, but from there, everything else is crap. So now what UBI does, it allows you to have volumes. You can resize them on the fly. You can, if you have enough free space, of course, where you can shrink them. If your file system still fits in, you can remove them, you can recreate them. So there's transaction safety built in to some degree. And what UBI does in the background, it's doing full device flash re-leveling. So back in the old days where you had these two partitions, one was your root file system, which was basically read-only or read mostly, and the other was your data partition, like some companies use that for logging, high frequency, high volume logging. And what happened is that we veered out that partition pretty fast, because we were just keeping on erasing blocks, rewriting them. So what UBI does, it spreads out the reload across the whole device. So if you have a 20 to 80%, 20% writing volume and the 80% read mostly thing, it still spreads out the reload, so the lifetime of your flash is going to extend. And that's becoming increasingly more important, because now with multi-level cell flash, from the worst stuff we get today, you're down to something like 2,000 erase cycles per block. Not many. UBI does bad block handling, and it has data integrity mechanisms. One of the mechanisms is if some client of UBI, maybe it's just something dumping the data out, or file system reads data from the flash, and there's a bit flip detected by either one of the error correction mechanisms there is either Hamming codes, don't use that anymore, it's not working on the contemporary NAND flash. I mean, it works, but it doesn't help, because the probability that you get more than a bit flip in 256 bytes of data is extremely high. So today, what you want to use is either read Solomon or BCH. Contemporary SoCs come with a built-in controller which does that for you. The real good ones actually have error correction as well, not only error detection. So that makes the life for the kernel easier, because doing BCH or read-Solomon software is extremely expensive. So, but once we detect a bit flip, then silently UBI, or there's some interaction with UBI Fast where you can ask offload that task to UBI Fast. But in a general case, what UBI does, it copies the data of that block where it detected a bit flip into an empty erase block, erases the affected block again, and recycles it as a fresh, usable erase block. That's data integrity. It has scrubbing built in, so you can even read out all of the blocks over time, just to make sure that the data is still correct here. And the problem is, you might not touch an erase block for a very, very long time, but due to the nature of NAND flash, stuff gets affected across blocks. So you're writing or erasing block A, and the neighbor block B is going to have bit flips. It's just how NAND works. And it's not going to go better with multi-level cell flash. And the structure sizes, we're down to 22 nanometers now, do not help either. So, that's just the usual. People claim it's a flash translation layer. It's not, because we have the clear notion of volumes. So this is two volumes. We have one with 3 blocks, one with 6 blocks, but one unmapped block. So, for example, if you have a file system volume reserved for 100 megabytes, and your file system actually only uses 20, then the blocks are not mapped. They are just kept as reserved, but they are integrated into the relabeling and all these kind of things. So that's always UBI does magic for you. Then, as you can see, the black one is the bad one, and the others are mapped across the device, so it's red. So how UBI does that? UBI cuts off a header-sized area from each erase block. So it basically reduces your usable data area. That's the price you have to pay for data integrity. So the metadata is two things. It's an erase count header and it's a volume information header. The erase count header is what we use for relabeling purposes, and the volume information header is basically how to identify to which volume this particular erase block, flash block belongs, and what's the logical number inside of that volume. And it has version counters for data integrity, so UBI can copy a block in the background, incrementing the version count, and it can deal with multiple concurrent versions, so it finds out which one you want to use. So now comes the downside. Back then when we implemented that with IBM, it was an IBM-sponsored project because they wanted to use NAND flash for their embedded controllers and servers. And if you break a server just because your flash update failed or your flash got bad, it's a pretty bad idea if you think about those huge transaction servers where you have something like 1 million transactions per hour or more. Those customers do not like brick machines. So basically what UBI does on attach time, it goes through all physically erased blocks and scans the headers. And then it builds all the volume tables and all these kind of things. And the mapping between the logical erased block number and the physical erased block. knows which blocks need to be moved around, and all this kind of information. So as you can imagine, this is slow. So the attach time is strictly aware, and it grows linear with the flash sizes, which was not a big deal back then because, I mean, the NAND flash they were using back then in the IBM project was about 64 megabytes, so it was not a huge amount of pages to read. And compared to the overall boot time of the server machine, it doesn't matter if you take a second more. So the attach time, you simply can do the math. It's the number of erase blocks you have scanned, the time to read a single flash page, and the number of header pages. So there's certain types of flash, and it also depends whether you're using hardware ECC or not. But in certain types of flash, we can split the write into a page in two chunks, which allows us to only use one page for the headers, which speeds up, of course, attach time, but it also reduces the loss of storage space you got. Technology hates me. So, yeah, I hate technology as well. So let's look at a simple example with 64 megabytes, 1024 physical erase blocks, and 512 byte page size. So we can assume that we do that if we fit the headers in one page, we can write to that page twice. So the total is 1024 blocks to scan, 50 microseconds for the page to read, and one page, so that's 51 milliseconds. Not bad. Now, this is a different thing. We have that today, 4 gigabytes. So it has 8,192 physical erase blocks, 4K page size, and we only can write it once. So we have to use 2 header pages, which means we take a whopping, if you assume the 100 microseconds, that's actually, you can achieve that if you have the right NAND flash controller, but you can assume that most controllers cannot do that, so double that number for a 4 gigabyte flash. But I was assuming the best case, so it's still 1.6 seconds. Hey, that sucks. It sucks in various environments, especially if you think about automotive. Automotive wants to be up and running in less than a second and be responding on the core bus. Yeah. Can we be smarter? Yeah, back then when we designed the UBI, we knew about that, we should be smarter about that, but there was no budget in the project, and of course IBM wasn't interested. And they were, but no budget. So, store the metadata, which is the header information, in a special volume. So now, you have that small problem, there is no static storage space in NAND. So we can't say the metadata is going to be in physical erase block number 1. No, it can't. Because we do not know if physical erase block number 1 is actually good or bad. It also prevents us to do cross-device view leveling and things like that, and it breaks a lot of assumptions we have to make about NAND flash. So it would work on NOR flash, which is a reliable technology, but it's slow. The storage size to price ratio is way off from what you are seeing on NAND. So, but yes, if you really care about your data, think about NOR flash, or at least about battery backed up SRAM, because NAND is not really good for data you care about. So one other problem we have, we don't want to write metadata whenever we do something to one of the erase blocks, because then you basically double the rear on your device, because each time you rewrite the metadata, you recycle a block. And one of the other concerns was, and there was a previous approach by, I think it was Samsung engineers, they tried to totally get rid of the header information. But I violently disagreed with them because it removes a lot of the data integrity built-in restrictions and mechanisms of UBI. So the idea was find a way how to find that metadata rather fast, but even if it's not there, okay, go back and scan, but you won't have a brick device. So that was the basic design assumption. So, how to find it fast? We split it into volumes. This is for those that are not exposed to the outer world. You can't mount them or attach to them. It's just internal meta volumes. So one is the reference volume and one is actually the data volume. So the reference volume is that what we really do not update very often. We only update it if you write a new metadata block. So then it contains only the information where is the physical erase block, where you can find the actual current metadata. And then we made an interesting assumption. We said it's going to be located in the first n erase blocks. N is depending on configuration and on the actual number of flash blocks. So it has to do with re-leveling constraints and things like that. And of course, we have to find it by scanning. Nothing to do about that. The data volume actually has all the mapping information. All the metadata we can read out of the headers, and it's basically a condensed UBI header. So, still, we retain the headers for sanity reasons, and we can recreate the metadata at any point in time. So you can even run today's UBI with the Fastmap on some old device which is not having a Fastmap volume, it just scans. It works. So we want to avoid the fast updates. So what we came up with is actually, if you look at the flash usage, we already had a kind of a pool, which is the number of erase blocks which are with the low erase count, which we are handing out for writing and getting them back for erasing. That's mostly what happens on the file system level. So we do have metadata for all erase blocks except for the pool. And for the pool, we know the physical location of the pool blocks, and we go to scan them. Yes, some scanning is involved, but it saves us, avoids a lot of writing into the metadata block. And we did experiments with writing the metadata block every time, and it turned out to be a real disaster, performance-wise and erase count-wise. So no, pool is, I think, the right thing to do. We rewrite the metadata list only when the pool list changes. So if the file system decides, hey, we need more blocks and stuff like that, so or shuffles around data, then of course we have to rewrite the metadata volume. So the pool list is again a configurable number of erase blocks, but it has also to do with the flash size. And it's used for the current write erase operations. We hand it out to UBI Fast and stuff like that. So the pool list only changes if we do real leveling. So if we see one of the blocks in the pool has been written to erased, so that it went out into the range where there are actually blocks which have a lower read count, So we have to swap. So that, of course, requires that. Or UBIFS decides to write 50 new blocks. Great. We can't do anything about that. So one of the real things I'm scared of NAND flash and the unreliability. That's why I wanted to preserve the robustness and preserve the existing header semantics. I was not so worried about the backwards compatibility. You can solve that differently. But the only thing why we kept the headers is really keep it robust. So now, let's look how that works. So we have that Fastmap reference block, which we try to keep within the first n blocks. So this one contains the reference to the metadata map, which then gives us all the information about those blocks. And it gives us the list of the pool blocks, and we are going to scan those. So if we look at the thing we had before, we scanned everything, and that's how it looks now. So now the math is a little bit more complex. So we have to know the number of erase blocks, the number of blocks to scan for a reference volume, the number of pool erase blocks to scan, the number of header pages, the size of an erase block, the size of a page, the metadata per erase block, and the time to read a single flash page. So yes, go figure. For the 64 megabyte flash we had before, where we had the 51 milliseconds, we went down from scanning 1024 erase blocks to that level. So we have 16 pool blocks and the reference volume is tried to be kept in the first 16 blocks. Again, we have one header page. So we have to read 352 pages maximum. That's the upper bound. So that brings us down roughly by a factor of 3. And it gets more interesting if you look at the launch page, at the launch flash. So we go down by a factor of 10 because instead of scanning 8,192 times 2, which is 16K pages, we only read 960 pages, which brings your attached time down into a very, very reasonable time frame. So, the Fastmap provides a significant speedup. And the speedup actually grows with the flash size. For small flash, it's not that spectacular, but if you're really into looking into fast booting, even on small flash, it helps. Because, yeah, we have this strange requirements in automotive. You have to be listening on the core bus within 500 milliseconds after reset release. And you have to be responding within a second after reset release. And you have these other requirements like being up on a GUI in a second and things like that. So yes, their milliseconds matter. So I thought about a few other things we can do. We have that not yet, but we could do that, and it's easy. Metadata, we looked at the metadata information we store in the data block. It's actually very good compressible. And we have all the compression support there in the kernel, so we could do just run it through ELCE or zip or something like that. That would bring down the number of pages we have to read further, because this data is really compressible by a factor of 5 with a simple compression algorithm. So it reduces, if you go back to that number, the large blob, which we have to read out, is here. That's the number of pages we get out of here. Is basically the number of erase blocks times 96 bytes. That's the size of the compressed UBI header. So now, and then divided by the page size. So, but if you compress that by a factor of 5, it's way less data to read from that block. So, yeah, decompression takes time, but it's reasonably faster than reading a flash page. One other thing, what's stupid about the current setup of UBI is that bootloaders tend to read UBI as well, and then throw away all the gathered information instead of handing it over into the kernel. So we should come up with some reasonable way to attach that information to the kernel, like we do with initial renders or other things, or device tree or whatever blocks. So yes, that would really, really help. One other thing, what would be really nice if we had some non-volatile RAM on a system, and we have actually a customer system which has this nice feature. So what we did as an experiment, we put the whole metadata block into the NVRAM area, so our scan time goes down to 0. Questions? No, code. It was merged in Linux 3.7 in the RC1 cycle. It was sponsored by the Consumer Electronic Linux Forum, thank you. And it was designed and implemented by Linutronics. I mostly did some of the design, and it was implemented by Richard Weinberger, who's working for us. He did a great job. So now, questions? No questions, good.
So merger to 3.7 doesn't mean that it's actually production quality, or is it some still experimental?
Well, I mean, if we merge code which works, it's usually somewhere in between experimental and production. It's very simple. As long as it doesn't get exposed to a huge amount of users, you don't find all the corner cases. We did massive testing of it, yes. And we have it in semi-production environments around. I'm probably still going to wait a couple of months until I'm confident enough to ship it, but it's pretty stable. And it's not going to change the... so we already have a provision that we can support compressed metadata, so it's not going to change the on-flash layout. It's just having a separate information in the thing itself, which the code can detect, so you can run those versions on it. Yeah.
When you do test it, do you have information can you test whether you had a bug in your driver and wrote some bad data, or you did bad wear leveling and now the NAND is really dead? I mean, do you test until the NAND really has reached all the erase cycles? Can you do that?
We can do that. And we did that before.
How long does it take?
Oh, you can do it pretty fast. You just have to, so the way we did it, we basically created smaller partitions and then did the full write logging to it. Just high frequency data. And that burns out the flash in a couple of weeks. Depending on the flash type, if you have single level cell, it takes a couple of weeks. With multi-level cell, it takes 2 days.
Why do you put the first important block in the first end blocks and don't decide to start from the end of the NAND flash and go because a lot of time,
we could have went backwards, yes.
Yeah, because a lot of time the best part is used by the bootloader, so it's easy to find from the end and go back.
Yeah, I mean, it works both ways. So no, actually you both have, you do not have, if you do your design right, then your bootloader is not sitting in the MTD partition. Let me show you the picture again.
Okay.
So, because the bootloader wants to be in its own partition.
Yes.
Because you have the requirement for the bootloader is that it boots out of eraseblock 0,
Okay. So this-
period. And so you have to separate partitions so you can it update.
Okay.
But then, again, your data partition, which will then have the various UBI volumes, is a completely separate beast. And that's why we decided to put it in front. There's no real reason why you couldn't do it from the back. It works both ways. I mean, we start scanning from front for the first N blocks. If we find it nice, we try to look at the metadata and look at if they make sense. There's a COC on it. And if they do not make sense, we go scan further. If we do not find it at all, we just scan through the device.
What's the limits on the first N blocks? I mean, is there a minimum? So I guess it can't be one.
No, it can be one, yeah. No, it can't. No way. Yeah, you can define it to one, and yes, you will get a surprise.
But I'm
No.
concerned about like how big can it be?
So we figured out that for sanity reasons, depending on the flash size, so the numbers I gave you for the 64 megabyte, 16 is the lower limit. We thought it would be reasonable, and the upper limit is 64 to 128, depending on flash size and flash type.
Because I think that has a direct impact on the time.
Yeah, of course. That's if you look at the number here. Of course. So the time we only are interested in the number of pages to read. The total number of pages. So it's the numbers of erase block we have to scan to find the reference volume. So that's of course directly linear. The number of pool erase blocks, which is roughly in the same ballpark than the scannable blocks. We might have to extend that when we get more information about UBI-fast use cases. And then you have the header page, the number of header pages times this is the constant, mostly constant port. And then this is only the size of the metadata, how many pages actually the metadata gets. So we can do, so yes, you influence your attach time by playing with the number of reference volume, the reference volume scan thing, and by the size of the pool block. And we influence it whether we store data compressed or not, but we have no compression at the moment.
Is there any plans where the compression support at the minute, or are you going to, how far is that from that?
We do it open source style, we're waiting for the patches. Usually patches come in when people have the need to. So now for the project we were doing at the moment, it's okay to have the Fastmap thing first, and we didn't want to add another layer of complexity. So stuff which is complex, and it is complex. You want to keep it simple in the first place, and then doing the compression thing is not rocket science. Yeah. Somebody else?
The MTD FAQ says that the mechanism to separate the metadata into separate volumes is called UB2, or they call it their UB2. So is this UB2, or is that something different?
No, it's just an extent. I mean, yes, documentation somebody wrote what we do with UB2. Sure, no, it just builds on top of UBI, and it's just extending UBI functionality. So yes, it's UB2. If you need a marketing buzzword, it's UB2. It's UBNT.
I'm asking because for UB3 there's a different problem. which wants to be tackled, which is memory consumption. So the question behind that is, can we tackle that?
No, we didn't look at memory consumption at all.
But we could now go into that direction. Since
Yeah, but I don't think that it can do much about the memory consumption of UBI, to be honest. I mean, it takes, you need some storage space per erase block. You could even go further and do the mapping on the page, page-wise, which would even need more storage space. We thought about that. But that really explodes the storage you need in RAM. But the RAM consumption of UBI is not that big. I mean, what are we talking about? We're talking about the structure UBI handles or has in the kernel. It's, if I'm remembering correctly, it's 128 bytes per erase block. So that means it's a K for 4 pages? No, for 8 pages, for 8 blocks. So we talk about on a big device with 8,000 erase blocks. We talk about 1 megabyte. Yeah. I mean, if you have 4 gigabytes of flash and you only have 2 megabytes of RAM, then your hardware designer did something really wrong. And you can't do much about it. I mean, you need the data. Yeah. I mean, you could be clever and only keep some of the data and then reread it from the metadata block, but that's going to go to hurt your performance. Because once you get out of the pool, and you can construct use cases where you get out of the pool pretty fast, then you're permanently reading in, throwing away. It's not going to happen. And you still need the, then when you're reading it back in and recreating the metadata, you still need the megabyte. Yes, there was a question.
Do you know if there are bootloaders that support it already?
We are using mostly the first stage bootloader of UBoot, which has UBI support, and we are currently thinking about adding the Fastmap thing there. It shouldn't be hard. I haven't come around yet, but it shouldn't be hard. So, more questions?
This is probably stupid, but how does the out-of-bound data area fall into the whole UV picture? Somehow used or?
Oh, no.
Not at all.
Do not even think about out of band. So think about a flash page has a really odd size. It's 4K plus something. So because with today's NAND flash, you need all of out-of-band area for error correction. Period. No metadata there. That was the first idea back then when they came up with this totally stupid smart media format, but I basically put kind of fat on it, which is stupid by definition, but okay. They used the out-of-band data for metadata storage. And then, but back then, NAND flash was actually half as reliable. You got NAND flashes from the manufacturer, and if you got a whole production lot with a million, you had maybe 1% in there which had a bad block marked from the factory, or way less than 1%. Today, if you get a million, you're lucky if you find a 1% without a bad block. I mean, that's fact. This technology is crazy. It kind of works, yes, thank you.
Okay, so
Most of the time. I mean, if you know what you're doing, if you treat it correctly, if you use a good error correction algorithm, if you do the releveling thing correctly, and do the scrubbing and actually take care of all the most of the corner cases. Well, there are some other corner cases in there which UBI should fix. That's the partially stable bits issue on multi-level cell. We have an idea how to do that, but it's it's probably going to involve more surgery. And it's good. Bad news, it's going to increase over time again. Yeah, but you can build halfway reliable systems even with NAND flash if you really do it right. But don't go there and use ECC hamming codes anymore. Everybody who's doing that today, yeah, good luck.
So basically the idea is that the outer band area for the error correcting is somewhere underneath the UBI layer, right?
Yeah, so when you look at the flash page, you have 4K data and 128 byte of out of band, or is it 64 or something like that. So then you take your error correction algorithm, you chop it up in bits and pieces. That means usually the PCH or read-Solomon coders take 512 bytes data in a row, and then you get 8 bytes of ECC code. And then you have again, because you want to do a hardware error correction, you have to do the data, ECC, data, ECC, data, ECC scheme, because otherwise your hardware controller can do error correction on the fly. So it has to be the data. That's the whole thing about read-Solomon and PCH. You want the data and the syndrome stored in a row, so you can do it on the fly. Yes, that. And so you go out into OOB, and for the more sophisticated algorithms, you actually use the OOB up to the last byte. Yeah.
So how do you compare UBI with the algorithm inside the SD cards and implemented MMCs? So
the problem with SD cards and MMCs is, A, we do not what their flash translation layer and re-leveling controllers are doing. And based on experimentations, we know they are pretty crappy. So there's a reason why Samsung came out with a file system optimized for those. And those guys actually had the nice opportunity to talk to those guys who were doing the controllers, which makes life more easier, but we suspect that the information they gave us that way is basically confirms what we suspected, or what Arndt Bergman found out by timing attacks on those devices. So you can figure it out what they are doing. They have become a little bit smarter than they used to be. 5 years ago, we actually did an experiment. We took a CF card and wired up a signal tracer to the NAND pins in the CF card, and then we analyzed what they are doing. And hey, this was great. This was a great piece of engineering. Because what we found out, and it's if you have really the cheap, it was only applied to the really cheap CF cards and USB sticks, by the way. They all have the same controller, they just stick a different bus interface on it. But the controller for the flash itself is all the same. So what we found out for re-leveling purposes, they copied crap into internal RAM, then erased the block, and then copied back. Guess what happens if you rip out the device? Your full block of data is gone. And it can break those things that way. So you all know that the thing you rip out your USB stick at the wrong time, and it won't mount never again. And you can't even reformat it because they lost their own metadata information. Great! Thank
That's
you.
the purpose. They want to sell hardware.
Yes, I know. They won't, and they made us believe that crap really works, yes. Most people believe that, yes. Unfortunately. Okay, we have a minute left, so that's one more question. No questions, great, Peter.